Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. So we were looking at the self-similarity of the mean velocity profile of a turbulent flow, right? And we looked at essentially the mean velocity profile in the x-axis. Okay, now let us look at the lateral velocity as well and see if it's very interesting. Now is that when we looked at the pictures, we were really wondering how are we going to quantify this, what are the things we need to study, or what are the things we can actually measure, right? So now we've defined things like jet in terms of a round jet, so jet half width, mean central line velocity, mean velocities, right? Now so let us look at the lateral velocity, which is essentially in the y-axis. So just to remind you, or let me just look this up, right? So we have just to look up the axis system, right? So this is your axis system essentially, right? So you have x, which is really the axis of the jet, as well as the direction of u. Yeah, so the direction of u, and then v is this and w is this. So when I say lateral, I essentially mean this y axis, and this is the velocity that we're looking at, right? And the v component of the velocity. Okay, so now let us look at that. This is also an experimental result, right? So, and we realize that if we plot the velocities in a certain way, they become self-similar in the sense that they really depend on a single variable. This becomes important in something as random and unsteady, both in time and space, and chaotic as a turbulent flow, because any which way, anyway, we are dealing with many variables that this flow can depend on. So it really becomes important that maybe if we can cut down on a few, makes our life easier. Okay, so self-similarity is really a concept from there, and like we said discussed in the earlier class, this was first the proponent of that was in the boundary layer theory, right, and that was back in 1908. Right, so we've kind of, I think this was later on proposed by Zeldovich in some 30 odd years later, I think. Right. Okay, so if I look at again, this is from the Hossein LDA 1994 result, and this is how the plot looks like. Okay. Okay, so this is essentially the mean velocity in the y-axis, along the y-axis with respect to the central line velocity, which is along the x-axis. Okay, that's what we're considering. This is zeta, right? And this we discussed in last class, which is essentially right. This is a non-dimensional similarity variable. We found this out in the last class. Okay, so this is okay. Okay, so the plot we have is something like this. It's something like that. Okay, so this is a result of These are experimental results. Okay, so this is what it looks like. Now let us see what does this mean, right? So now we plot this. We just take the velocities and we plot that, and now we're trying to make some inferences which seem to have some physical implications, which is quite interesting, like we were seeing last time as well, right? Now this is a very interesting thing. Now let us see. Okay, okay, maybe this is a part which is a little. Okay. Actually, if I can do this a little better. Okay. Okay, I think that I like that better. Okay, this you can look up the plot actually. Okay, so this is essentially the, now what do I see, right? So if you see the maximum, velocity, actually, okay, I am going to draw this plot a little better. This is not looking okay. Okay, this is not looking okay. So yeah, I think okay, I think that I'm okay with that now. All right. Now the point is that that's the maximum 0.02, right? So if you see that, okay, so what is the maximum? So this is say the maximum, right? So this is the max, right? So here, right, this max value is about say 0.02, right, which is essentially equal to what? This, right? So you could, so this is essentially what we are saying is that this is also an important result, because we constantly consider only the actual velocity. We're not looking at the v velocity. We are anyway ignoring the w component of velocity, right? So I think it's important to figure out physically what that means, right? Physically what we're seeing is here v is, about 1/50 of the maximum of the central line velocity, right? So it is less, or you can, so if I were to sort of write this down, right, so this is less than the central line velocity. The mean lateral velocity, right, is less than the mean than the central line velocity by a factor of nearly 50, right? It's probably less than that, but between 40 to 50. Okay, so now, so in the sense that it is, it's less, because we keep ignoring it, right? So is it less enough to be ignored? I think that's the question we will look to answer. So yes, it is less than, the central line velocity, and it's not trivial. Now, what is interesting is that if you look at the v by v naught plot here, right, if you look at this, so let's just say, right, now if you see here this part of the plot, right, and especially say this, right, this is negative, right, here, say at 2, right. So at 2, zeta is equal to 2, right, which is r is 2 times the half jet half width, okay, the V bar by V naught is negative, which means, right. So, if the axis system that we looked at, right, so is such that the axis system, right, so V positive is along that axis system, but if it's V bar by U naught is negative, that means it is opposite of that axis system. So, in this essentially means that the flow is moving in a direction which is opposite, to the positive y direction, right. So, which means that if I were to sort of draw this, say like this, right, this is what we have been drawing so far. So, let us just say at some point, right, so at some point, so you will have this right, you will have this, the mean velocity, this. Now, if this becomes negative, right, it means if it is negative, then of course, what we mean is that the velocity is this, right, understandable. So, and x is of course coming out of the plane of the board, right. So, now, so essentially what we are saying is, and when you, so zeta is equal to 2, right. So, which essentially means that it becomes, at a point, right, and also at this, if you see here at the this location, say this location here, right. So, there is a positive value of the V, right, and then it reaches 0 and then it becomes negative, right. So, this is a point where we do not know what the, so the zeta is at this point, right. So, V bar by V naught is basically 0, right, it is 0 and then it becomes negative, right. So, this is essentially what we are saying is near the edge of the jet. So, essentially the fluid is flowing in the negative direction, which is into the jet itself, right, because the jet is flowing out, because we have been talking about the jet spreading, right, we were talking about the jet spreading. But if you see the V component of the velocity, right, what you see is that around the edge, right, around the edge, a little around that, right, the V component of velocity is actually negative, meaning that the flow is actually happening into the jet. So, this flow is actually happening into the jet right here, right, it is happening into the jet, and this is basically what this is called. So, what this means is that fluid is, well, yeah, flowing in the negative y direction, or I am going to, okay, fluid is flowing in the negative y direction, right, which means that the fluid is flowing into the jet, right, and technically this is called fluid is entrained. Right, entrained, and essentially it is being transported across the surface, right. So, entrained, or which basically means is transported across the surface, or rather interface, to be more precise. Yeah, so essentially fluid is, I would say, flowing into the jet itself, right? So the fluid is essentially flowing into the jet. It is flowing in the negative y direction, so fluid is being entrained. And all of these things, we have looked at pictures, right? What is interesting here is that there's so much back and forth between the math and the physical pictures and some geometry and then of course the analysis, right? And yeah, I think it's interesting to sort of wrap your head around all these things. Kind of, one feeds the other, so which is nice. So essentially, we've been talking about flow moving, and then it is spreading. The center line velocity decaying, so therefore the jet also decays. And now what we also see is that the negative, that there is also a lateral component of velocity which is actually entraining fluid. It is making fluid come into the jet itself. It is not very large in magnitude, so it is less than as you've seen here, it is less than u naught by a factor of 50, but nevertheless it is sort of trying to it is a flow velocity which is sort of bringing the flow into the jet itself. Okay, so I think what is interesting is we started talking about this when we started looking at this. Now we just went ahead and looked at some plots which are essentially just calculations in a lab setup, and then when you look at it, you're actually also, when you look at the plot itself, so this understanding that fluid is being transported across the interface into the fluid, is being entrained, is flowing in the negative direction, is all from actually a physical experiment. And then you take a result out of that, you make the measurements, and then when you look at the measurements itself in a plot, you're actually making this physical revelation about the round jet. I find that very interesting, because typically what we will start out by saying that, look, this is my flow, then how would you write equations for it, right? Is that here what we've done is we are actually calculating things in an experiment, plotting this result, and then when I look at that, I actually make these inferences which are actually talking about the physical the physical behavior of the jet. Okay. All right, so that's something. So we learned quite a few things, right, about the round jet now, right? So essentially, what we learned is that the round jet, okay, when it leaves the exit, okay, around the exit, about 25 times the diameter of the exit. It's called the developmental length, and after that, right, the jet spreads and also decays, right? We're talking about the strength of the jet, it also decays, right? And now we've looked at this and we see that there is also flow which is being entrained near the edges, edge of the, near the boundaries of the jet, okay? All right, so now moving on to some more math, I guess, right? And let us see. So we've made measurements, some understanding, etc. So let us say what else we can think of. Not yet. We've looked at the Navier-Stokes equations and yeah, right. Okay, so now let us look at this. So one of the very important terms, right, when we looked at the Navier-Stokes equations and we incorporated turbulent behavior into that by saying the velocity is a sum of a mean component and component, a fluctuating component, right? That's what we did. So now let us look at, so we ended up, that was a nice thing to do, and then we ended up with, some terms which seem to be quite difficult to compute. Okay, let's put it that way. So let us look at what I said to be, so Reynolds stresses. Okay. Now, so the Reynolds stress is essentially this term. The time averaged ui and uj, right? These are the terms. Okay. So essentially what we are, so this is a 2D picture that we are looking at. Okay. So let us see what this, well, not 2D picture, sorry. So I goes from 1 to 3 and j goes from 1 to 3. Okay. So this is the entire Reynolds stresses. Let us see what terms we will get, right? So this is obviously a tensor. So the tensor, Reynolds stress tensor, right, it looks like this. Okay. So essentially what I am saying is u1 is equal to u, then u2 is equal to v, and u3 is equal to w, right. So yeah, so the subscript 1 essentially means the x component, 2 means the y component, 3 means the z component. Okay. So if I and j is equal and it is 1, then this is u dash square, right. So similarly we will have v dash square and we will have w dash square. Okay. That. Then we will have u dash, v dash, right. Okay. Then here it is nothing but v dash u dash, right, and this. Okay. So definitely here we will rule out the w. So we are going to ignore that. Okay. So we are going to basically say ignore, right. So essentially we are basically saying, because we are dealing with the fluctuating part, so we are going to say the fluctuations are primarily in the x and y directions, and the z directions we are we are basically taking the same picture as I move along the x direction, right. So we ignore that. So therefore it is statistically 2D. So what we are considering is a 2D. Okay. So therefore if I rule out the w dash, right. So if I rule that out, okay. So then this term is 0. Okay. Okay. And we'll still have that. Okay. We'll see. Right. Okay. Now, okay. So what I meant here, I should have written that, I think. So yeah, this is fine what I've written here, but what I meant is this. Right? Okay. Okay. So now we will jot down a few things. Okay. Now circumferential, so UW, right, and VW. So UW and VW. Okay. There are terms like UW, right, and terms like VW. Okay. Now these things, so as you can see, so again U dash, this is just, so this term and this term is actually same, this term and this term is actually same, right. So this term and this term is also actually same. Okay. So okay, when I said this term, so basically I mean this and this is same, this and this is same, this and this is same, right. So so this is, so circumferential symmetry. Okay, how to explain that? So U dash W and V dash W. Okay, so in the sense that you have the U component. So the U component is, say, somewhere in this direction, right? This is your X, and this is your Z component, right? This is your Z axis, right? Okay, and you have your, say, U in this direction, this fluctuating part, and you have W in this part. You have W in this part. Okay, so now what we're basically saying that if I take, because this is a round jet, because it is a round jet, right? So okay. So yeah, I could have drawn this a little better. So essentially what we are saying is that across this one, right? Okay, so one half is here and the other half is here. Okay, in this round, in this round jet, and they kind of mutually cancel each other because they will be symmetric, but in different directions. I don't know if I'm able to explain that right. Okay, so essentially what I'm trying to say is, this is the exit, right? Let's just say this, right? And you have this is your X, right? And so you see I have one half, right? So, and also, right, and this is your negative X. So essentially what I'm saying is we take sort of one half of this, right, on one side, right, where we will have, say, U dash. So there I will essentially have something like on this half, say I will have U dash this, right, but on this half, right, on the other half, right, I will essentially have right a negative one. So this is along basically Z axis. So therefore, if I take the mean of that, it will get cancelled. So this I'm basically saying there is circumferential. So within this, because it's a round jet, so therefore this is like we're taking into account of a symmetry. Okay. So similarly, if I have V dash and W dash, so in that case is nothing but, so actually I should just sort of erase this part, let's just erase this part. Okay. Okay. So, that is that. Okay. So, then I could again have something like this, or let us just say I will, okay, I can just do that here. I think I will do a smaller that, okay, and the axis system again. Okay, actually I do not need that right now. I am going to draw just the, okay, I am going to draw the V actually. So, this is my right, and then this, right. So, again you have V dash and W dash. So, then I have 1/2 like that. Right, and you have the other half like that. So, essentially what you will have is that this is say V dash negative, and what you will have on the other side is essentially V dash and W dash, which is positive. So, that is why because of the symmetry these terms kind of cancel out. Okay. So, the total, if I sum that out, because I am taking a mean, right. So, I am going to cancel that out. So, that is what essentially is what we are doing over here. So, we cancel out these terms. So, it is essentially invariant as I move because I do not, it is invariant along, when I say ignore this, I am basically saying that ignore the changes in the z direction. Okay. So, ignore the changes in the z direction. So, if I have a picture like this, right, if I have a picture like this with a certain x velocity and y velocity, I basically repeat that along the x axis, along the z axis. Okay. So, it is invariant. Okay. So, from that that way of looking at it, so these are the terms which will go to 0. Okay. Now, geometry, okay, so here this is something, okay, geometry, which is a round jet essentially in this case, right. It dictates that the normal stresses are even functions of R. Okay. So, what this dictates is that the normal stresses are even functions of R. Okay. Well, R, but then the UV, okay, this is a little bit of a math part where I guess you will have to brush up your math a little bit before you sort of do this. Okay. All right. So, UV, this is an odd function, right. This however is an odd function. Okay. And at R is equal to 0, of course, at R is equal to 0, what do you think? At R is equal to 0, right. So, V and W components are indistinguishable, right. There is nothing, there is no difference between V and Y in any case, right. So, well, that is that. Okay. So, I think I should write that. So, that's UV is an odd function, and at R is equal to 0. Okay. Well, we can just say that the V dash and W dash are indistinguishable. So, basically they are same. Okay. Okay. Now, which is, well, I mean, The point is that if that is so, right, the reason we did not take out this term w dash square, right, because we said it is indistinguishable, then how is it different, etc., etc. But the point is that when r is 0, these two are anyway indistinguishable, which essentially means that this is equal to this. V dash square is actually equal to w dash square. Okay. So, therefore, we could not take out this, even though we have similarity, symmetry, and along the z axis there is nothing changing, but still we did not take this value out, whereas these are values that we were taking out, right. So, that is because at r is equal to z, these two are not any different, and then this, if you square them up, then these two become same. So, then this term is not indistinguishable. Okay. All right. So, we have that. So okay, let me, sorry to go back, I will just go back once and just write here. So, therefore, so this essentially means that v dash square, right, is equal to w dash square. Okay. Okay. All right. Now we will basically do this. Okay. Now, RMS of the axial velocity, root mean square velocity, right, axial velocity on the central line. Okay. So, that is nothing but okay. So, now we will ask a couple of questions. Number one, okay, we are going to pose these questions, you will see why. Okay. How does with x, okay, or okay, vary with x by d. Right. So, we take the RMS of the axial velocity on the central line, and we are calling that as u naught x, right, u naught dash x. So, how does this vary with x, or if I take a ratio with the central line velocity, how does it vary with x by d, right? That is what we are trying to see. Okay. So, what is interesting is, I think I will answer that question now and then sort of look at plots later on. Okay. So, what do you think is going to be answer? Well, so after the developmental length, which is x by d over 25. Okay. So, this u naught, this value, right, this tends to about, this value tends to about 0.25, right, and there is no systematic dependence on RE. Okay. No systematic dependence on RE. Okay. So, it seems like it becomes self similar, we are looking at x by t, right. So, essentially what we are saying is if I do this. So, if I have this, right. So, RMS is this. So, if I have plots, so this is v dis u naught x. So, dependence on RE. So, which is essentially now all of this essentially means that the Reynolds stresses becomes self-similar. Okay. So, essentially if I were to do right, okay, and we plot this and you plot this against R half, right, or right, then they all collapse onto the same, they collapse onto the same plot, like for x beyond developmental length. Okay. So, essentially if I plot this, this, right, against this or this, they collapse onto the same curve essentially. So, which is essentially what that means is that they are essentially self similar. Okay. So, okay, if I were to go back just a little bit, so talking about, so essentially what we found is in the last class is that the mean central velocity is self similar. Okay. And now we see that the Reynolds stresses themselves are also, so we took a 3D space etc., and statistically 2D velocity profile, and they also become they are also self similar. The Reynolds stresses are also they are also self similar, right, and there is no systematic dependence on RE, and something like if you take the RMS, okay, of the axial velocity on the central line, right, that value is about 1 by 4. So, or say the velocity u naught dash is about 1/4 that of the central velocity. Okay. Or basically the RMS of the axial velocity in the central line is actually about 0.25 times the central velocity. Okay. So, now okay, I do not know if I want to start this today, but the point is that there are certain physical, now that we have studied the round jet for a little while, we have looked at pictures, looked at done some math and looked at a few things. Now, see, this just irrespective of what we are trying to understand, if we can avoid solving if you can do this in an easier way, it will make our lives a little more easier, then why not, So, from that context, now the idea is that the round jet has several physical features, right. It so happens that if I were to jot down those physical features, you could easily say you are talking about a boundary layer, right. So, unless and until I tell you that this is I am actually talking about a round jet, you would actually think that these physical features actually also exist in a boundary layer. So, then the question is that if that is so, if the physical features are so, so the computer code is not going to know whether you are talking about a boundary layer or you are talking about round free jet. Then what's wrong if I use the same equations that are in boundary layers rather than the full Navier-Stokes equations, which for turbulent flows. Okay. So that is essentially the objective, and so in that context, let me write down a few salient points about what makes us do that. Okay. So that's what we will sort of do that. Okay. So I'm going to say these are boundary layer equations. Okay. Now boundary layer equations. Okay. So what the physical features that I'm going to write down now is really about a round jet, not about a boundary layer, right? But let us see if you can find any similarity of that with a boundary layer. Okay. So in a turbulent round jet, right? Now there is a dominant mean flow axially. What else can I write? So there's a dominant mean flow in the axially, that which is essentially x-axis. Yeah, axial direction basically, which is the x-axis. So it depends. I mean, how you arrange your axis system, it's fine. But what we had done is we had the x-axis going along the axis of the jet, right? So there is a dominant mean flow actually. Okay, the mean lateral velocity is literally very small, right? The mean lateral velocity is very small, right? So we have written that down. times the central line velocity, right? So what did we, let me just go back and see. What did I say it was? Yeah. So you see mean is about 1 by 50 of the central line velocity. Right, it is very small. Okay. So the flow spreads, but it does that gradually. Right, where okay, this is the spreads gradually, and the actual gradients for mean quantities are small compared to the lateral gradients. Okay, so so essentially what I mean here is the axial gradients of the mean quantities, mean of the mean quantities is small. It's very small compared to the lateral gradients. Okay. Okay, this flow spreads gradually, and we are going down the x distance. So, in the x distance, this axial gradients, there are gradients of, say, the velocity, for example, or pressure, temperature, etc. So, that the gradient in the x axis is smaller compared to the the y axis, the lateral gradient. Okay. So, we say it spreads gradually. So, okay, right. Now, this pretty much this kind of, so this is something based on this kind of a behavior, right, where you actually have a a flow like that, okay, and this v component, this is say a u component of velocity, and the v component of velocity is very small, okay, and the actual, so essentially the gradient, okay, of velocity in this direction, for the boundary layer is essentially in this direction is smaller compared to the velocity, the gradients of the quantities in the x axis, right. So, pretty much for these reasons, these are also similar features, these are exactly the similar features which are also applicable to a boundary layer. Okay. So, we will take it up from here in the next class and see that what exactly we bring into the turbulence, understanding of a turbulent flow by means of using boundary layer equations, right, and how that would, what does this physically mean, because when you input things into the computer code, you just input numbers. Okay. Now, how are you going to represent a turbulent flow from there, in a round jet, or a boundary layer over a flat plate, right? So, I think that would be interesting to see. So, I will stop here and take this up next time. Okay. Thank you.